Si è spolverito. Sì, sì. Ok. Va bene. Cominciamo. Scusa un attimo, c'è Sì, comunque va bene. Cominciamo allora. Okay, so we can start, I think. Good morning, everyone. I have the pleasure to introduce you, Robert Antonucci, 100% Italian DNA, coming from the University of California, Santa Barbara, and as you probably all know, he's the guy of a unified model of AGN. So,
that's good enough.
And today he will talk to us about AGN and Quasars. So,
yes, I'm honored to be here. I did have my DNA tested, and my parents told me the truth. I was pleased to confirm that my DNA is 100% Italian. Enrico and Marco visited me last summer, and we had already elected Caligula, and I thought, and Marco told me that I have the right of return to Italy, just like the Jews. And I thought, well, if things get bad, I will surely come to Italy. And now you have elected, what, I don't know, Nero, what emperor is most similar to your emperor. I'm depressed about a lot of things, actually. I'm depressed about that. I'm depressed that I just had to explain climate change to my Astro 1 students, that Venus gets absorbs less starlight than Earth does, and it's 900 degrees Fahrenheit in the surface. But whatever. I'm depressed that I ask informed, intelligent people, give me some hope on climate. But I can't find any hope on climate, and we're throwing the planet away. I don't understand that. Things seem extremely dire to me. I go to my students, and I was told in Physics Today there was an article called "How Not to Teach About Global Warming," and it said, do not tell your students they're doomed, or else they will take no action and they'll just be depressed. And I thought that was good to hear, but I'm torn. We become, in science, we become pathologically, intellectually honest. And I think I know they're doomed, right? And I don't know how to say that in a way that makes it sound cheerful. And our policies in the U.S. are out of this world. The more methane, the better. Whatever happens, happens. I'll make you the same deal that and I'm depressed that a subplot of my life has become more and more, will we have a predictive theory of quasars before I die? Now, I'm just being very morbid about this. I don't know why, but these things I'm afraid to look at the news and see who our new Supreme Court justice is. I'll make you an offer that I make my Astro 1 class. That is, I make them the offer that if I say something wrong, then I give them $20 if they can show it to me. And they pick up their ears, and it tells them a couple things. It tells them that I care about what I'm saying, that I have some confidence in it, but really, to me, it's well worth $20 to have one of my misconceptions rooted out. I must have many misconceptions, and I would gladly pay $20 to have each one rooted out. I hope you can collect some of this money today. I am running as an observer. I am running out of ways to ideas for solving the quasar problem. And I am thinking, we can hope that the numericists in another 50 years, they'll figure it out, or the extraterrestrials will tell us. Very pessimistic about it. The things that some people think that we know about quasars are that the big blue bump comes from thermal emission from an accretion disk. What's the basis of that assumption? Nothing. They don't behave the way they should be in terms of their dependence on mass, Eddington ratio. Most telling of all, the most important characteristic of a black hole as it's modeled today is that the emitting area has a finite size, and the emission follows the potential gradient. And we know now that that's completely false. If you believe in reverberation sizes, or if you believe in microlensing sizes, the emission doesn't come from where the potential drop occurs. And in all models, it does come from where the potential drop occurs. So I don't see how they're even close to being on the right track. And the other pillar that I was excited about for a few months in 1995 was the K-alpha line as reprocessed fluorescence in a thin disk, and I think that most of those papers are very weak, and they use razor thin disks for super Eddington sources, and they allow themselves so much freedom since they discovered that instead of cross-correlating the signal between the line and the continuum, you could do it all in Fourier space and select particular temporal frequencies to correlate iron changes with continuum changes, and so you have that freedom afterwards. You pick afterwards which lag you want. There's just much too much freedom there, especially since many of the practitioners have taken a lot of freedom in past projects and I would say abused it. So I have taken mostly to complaining. I don't have any great new discoveries for you, and I'm going to complain that people don't think critically. I claimed in a Nature paper that was on the 50th anniversary of quasars that almost all theory is ruled out by the time it's published, and almost all observation is interpreted in terms of falsified models. And I feel like I'm going a little crazy. I I will also tell you at the end, if I have time, about a dirty little secret. There's an observation I published 20 years ago, and we've all quietly sat on it because it's either a huge breakthrough or wrong. And I'll show it to you if we have time at the end. I hope we don't. Okay, I'm also going to complain that everyone doesn't do polarimetry. On many telescopes, the polarization comes for free. And on many telescopes and in many observations, spectral and imaging in the infrared galaxy arena and in the quasar arena, you learn so much more. And people just, oh, let's move the polarization optics out of the beam. The VLT has a beautiful polarimeter, as does the Keck, and they'll move that out of the beam. I think that a proposal for those telescopes should have a box, and the box should say, check if you would like to have the polarization optics removed from the beam, justify below. And because it's free, essentially. Radio astronomers, of course, get polarization, and they don't say, before you send me the observation, scramble any polarization information. But that's how we do it in optical, even though history shows that it's so rich. Okay, now I'm going to show you some, the central engine spectrum and size. The big blue bump is the energetically dominant component of the quasar spectral energy distribution. And most people say it is from the accretion disk, not an accretion disk, but the accretion disk. Can you think of any arguments for that? I can't. I can think of one that it's thermal emission, which I'll show you. But it doesn't obey any of the rules that we like the Stefan Boltzmann rule. I say that if I say, what do we know about quasars, and now I'm going to set the level high and say, what do we know about quasars that's really important, and we really know it, and it's really interesting. And I'd say, setting the bar that high, there's one thing that in 1969, Lynn and Bell predicted that we would have huge compact masses at the centers of galaxies, and that turned out to be true. And to this approximation, I would say we know one thing about quasars. And we know two things about stellar mass black hole accretors. We know that they have compact masses of the right order, and we know something wonderful. Let's see. We know something. Okay, central engine and spectrum size. I'm not super organized, I'll tell you. Without Enrico, I would have been a mess. Why we make no progress in this field? Because I was really depressed putting this together, a unified model. All right, I want to show you something that they have. Look, here's our theory for quasars. I think when I started out 30 or 40 years ago, we had the same theory. The part on the left is, in order to get the big energies and energy densities, we need this, this, and this. And then on the right is the phenomenology, and that's what's in between. And okay, this is what I want to show you. If you work on stellar mass black holes, you find out something wonderful. You find out, according to Gerlinsky and Dohm, that in the efficient part of the accretion rate range, the temperature knows about the luminosity. The temperature follows roughly luminosity to the 1/4 power. The thing about a quasar is it's a purely geometrical object. It has a size of a potential well that's well defined, and it doesn't change from 1 week to the next. Look at this. When Christine Doan visited us in Santa Barbara and showed us this before it had come out, us being me and our theorist Omer Blaze, it changed my world, because I thought, okay, something is true. Something is true. And he soon after that said to me, and I think for this reason, AGN make no sense, I'm going into black hole binaries. And if we had this, but this totally doesn't happen, nothing like this happens. So we don't have thermal emission from a fixed area. But no one cares that much, I guess. Let's see. Okay, I want to find out the true spectral energy distribution of a quasar, because when you observe a quasar, you find that it has atomic features almost all over it. H beta, or H gamma, H beta, and O3, and pretty soon you have H alpha and other lines, and then all is lost because it rises into the infrared because of the dust bump, from which I would dare to say, roughly speaking, I'm not dogmatic about this, this is a torus emission, so if you said to a theorist, would you model this, please? Here's 1 point, here's 1, and maybe you could take the one at 1 micron, and then if you go below 1800 angstroms, there's some relatively clean spots, and then there's nothing beyond that when you get to the Lyman edge. So with my postdoc Kishimoto, we noticed that there are some quasars that have a little bit of polarization, and this polarization is from Thomson scattering inside the BLR and inside the dust emission. So the polarization in the unified model takes place on scales of parsecs or tens of parsecs, but now we're going down to scales of 100 Rg, and we find there's another mirror. There's a few electrons that are predominantly in the plane, not in the polar direction, predominantly in the plane because they give a polarization parallel to the radio jet, and the polarized flux looks exactly like the total flux, except for without any junk on it. And so, first we were interested in the Lyman limit, because predictions were that if you have a positive temperature gradient, you would have a Lyman edge in absorption, according to Kalikolov and Sinyaev. And that's pretty uncertain, but we thought we would explore the Lyman edge anyway, because it has so many things going on there. The Lyman edge is you could ask yourself, one, there's Balmer continuum emission. Why is there not in one quasar ever Lyman continuum emission? Now, you can, with optical depth effects, you can sort of get rid of it by fine-tuning, but it seems weird to me that we never see anything at all. Another thing that we never see at all at the Lyman edge is, even though the broadline region has a covering factor of 30%, none of you have ever seen a recombination emitting broadline cloud in absorption. If the clouds were smaller than the continuum source, all continua, all composites, which show 30% decline at the Lyman continuum, the Lyman limit, and they don't. And if instead it were if the clouds were big compared to the continuum source, you would see 30% of quasars that were wiped out at the Lyman edge, and no one has seen anything like that. So the only logical explanation for that is that all sight lines that pass through broadline clouds drop out of the sample, and the only easy way to drop out of the sample is the same sight line must pass through the torus. So we put that with the radio galaxies. So that's okay, but it bugs me a little bit that nature is quite that neat. I feel better about it if I say the broadline region is a part of the, is what we call the part of the torus interior to the sublimation radius. I've just rephrased it, but that makes me feel a little bit better somehow. Another thing about the Lyman continuum region, I'm rambling, I'm sorry, but there are so many papers in the literature, countless papers that invoke external illumination, because the timescales of variability in the big blue bump are ridiculously small compared to the viscous timescale or the other timescales in the problem. And in fact, it was shown by Krolik's group in 1991 that the coherent variations between wavelengths in the continuum are, any lags between them are so small that they must speak to each other at a speed with a message that travels at a speed of at least 0.1 c. So on comes the external illumination. There was a whole industry of external illumination for Seyferts, which I thought was kind of ridiculous, because with Seyferts it's marginally energetically possible to do this, but quasars have the identical problem, and it's not possible energetically to do it there. But also, if you ever invoke external illumination, you should be required to cite a paper by Krolik and Sinsel, which enforces what is really a commonsensical thing, and that is that you'll produce a Lyman edge in emission. And it's never mentioned in any paper that invokes external illumination. So I feel like I'm going crazy here. How can that be? I mean, they didn't just write that paper for fun. Okay, let's go back to this. What's the true spectral energy distribution of the central engine? This little thing here gives you the idea that if you want to get rid of the emission lines, all you have to do is plot the polarized flux, at least in favorable cases. And the original name of this talk was Soraze la barbe, which I was told means shaving your beard. And you can shave these lines off. Now, look what polarization does for you. All of a sudden, you actually know what the central engine looks like. And I cut this off here on this slide as a tease, because after we found that absolutely nothing happens at the Lyman edge, the Lyman edge region in disk models is unstable, and it's broadened, and it's easier to hide an edge, and the constraints you can put on an edge due to intergalactic absorption are weaker. So we thought we have to do the Balmer edge, but in the Balmer edge, every single quasar turns up drastically at 4,000 angstroms, supposedly because of overlapping broad Balmer lines. I've never really played with that to see how well that works, but I guess I'll believe that. But the point is, you can't look for what you really want to see. What you really want to see is if this is an optically thick emitter, then there should be absorption in the Balmer continuum at least, which is way out in the purely absorptive and non-relativistic region of the disk model. So do you see the Balmer edge in absorption? And the answer is, yeah, I think you do. Here, this is going up. It's a little maybe hard to tell. It's certainly, this is polarized flux scattered from the central engine. So this is the quasar spectrum. This is not the quasar spectrum. This is the quasar spectrum plus an enormous amount of reprocessed stuff. If you really want to know what the quasar spectrum looks like, you have to do this. And the reason why I tended to believe that this really is a break is, one, I didn't do it. My postdoc did it, and he never makes a mistake, Kishimoto. But the other reason is that they all look the same. Here is this 4,000 angstrom region. In total flux, they all have the famous small blue bump. And in polarized flux, they all dip to 1 degree or another at 4,000 angstroms. Each one, if you plot them individually, they look like smile shapes. So that suggests to me that it is optically thick thermal emission. And then we thought, let's find out what the big blue bump does longward of 1 micron. Because no one has any idea, because there's dust there in every case. And so we found some dust, some quasars that seem to have unpolarized dust. Here's the total spectrum. It reaches a minimum in nu at 1 micron, as you know, and then it goes up, and that's supposed to be from dust at the sublimation temperature, and we know it's true from dust reverberation and interferometry. What does the big blue bump do? It does this. So you can measure the spectrum of a quasar, but no theorist basically has shown any interest in the actual spectrum of a quasar, only in the observed spectrum of a quasar. Let's see, how am I doing for time? That's the halfway mark, so the answer is not well. Okay, well, we're going to go a little bit faster. Oops. Okay, how big is the big blue bump? In the black body model, you know its precise solid angle. Only trouble is, it's really several times larger if you're to believe the microlensing people, or the people that do reverberation, and they think they see the X-ray echo in the optical and UV. How big is it? It's small, but typically it's a factor of 4 larger than average from the thin disk model based on microlensing. The microlensing is heavily attenuated relative to what one would expect from a black body disk. But this had essentially no effect on the theory community. There's only one toy model that I know that takes this into account, and that is this one by Dexter and Agel. So this it's shocking because it means it's not just optically thick thermal radiation. 2, it's shocking because it means that the energy does not come from the potential drop region. And there's no model that even addresses or mentions this except this toy model, that either this microlensing is crap, but it was confirmed supposedly by reverberation, or, you know, everyone is still making models where it's a black body, a solid black body with, and that the energy comes from where the potential drop. Well, the only reason I take this seriously is because It's been going on for many years, and this is the average of many objects and many groups. And I'm no expert on this, but then it was confirmed by reverberation. So it seems relatively robust, but it has no effect on the theorists. On the other hand, I just told you that there is that clue that the big blue bump has optically thick thermal emission because the Balmer continuum is in absorption, like a star. So now I've said a contradictory thing, that it is and isn't optically thick thermal emission. The only way to get around that is the way they do essentially. In their model, essentially, their disk is not filled. It's mostly empty. You can mostly see through it, or at a given wavelength. They have sharp temperature fluctuations, so that their disk is made of spots. There are some numericists who are making disks that look a little promising, that their disks are made of spirals with low covering factor. Well, anyway, these relatively robust arguments tell me that quasars are 4 times as big as thought, and maybe they are optically thick thermal emission, but their filling factor is low. And that's not in the physics of any of the models. Let's see how far behind I am. I'll just take 1 second. Okay, here's where I have decided, I've not consciously, but somehow I've taken on the role of being the person who, the whiner, of astronomy. I'm complaining about all this stuff. I was looking on the Facebook AGN page, and Andy Lawrence says, changing look, AGN, they change fast enough to preclude the quasistatic disk model that everyone has been using. And that pissed me off. And then what was more was like there were 30 likes. And the reason why it really irritated me was because, not because it's wrong, but because that was known and clearly explained 30 years ago. And it's like now it's 1980 again. It's like we start over every day. We forget everything we know, and we start over and we discover the same things. And especially in a paper by Aula in 1985, they explained very carefully that the fact that the optical H-beta varies in exact phase to their ability to measure with the optical continuum means that the ionizing continuum varies in exact phase with the optical continuum. And that means that those putative radii talk to each other at light speed. But I have said this in many papers, and many others have. But, nobody reads the literature, or if they do, it's just one of those things. And I don't know, it just irritated me, so I wrote that. Okay, that's the disks. Okay, here, now going to the unified model. Here, let's see, tell me, I got to figure out how I'm doing on time, sorry. It's 12:05, and let's see, how far? 15 minutes. 15 minutes? Okay, thank you. So I'm sorry to be such a bummer, but it's just my frustration and the fact that I can no longer tell myself we're going to understand this before I die. Okay, the unified model, this is from 1980 or so, and it's the radio galaxy 3C234. Here's the smooth spectrum. This is the discovery of the reflection and the torus and so on. Here is the 507 line, which is a forbidden line. Here's H alpha, which is a permitted line. And here are the Stokes parameters not normalized. They're not in percent. This is just the light in the 0-degree ray minus the light in the 90-degree ray. And this is just the light in the 45-degree minus the light in the 135-degree ray. And you can see that there's no big thing here for the forbidden line, but there is a big line for the permitted line. And that tells you that this one, that the H alpha line is highly polarized and the forbidden lines are unpolarized. Okay, so it's the permitted lines that are hiding inside something. And the position angle of the polarization, which reflects the photon's last flight before being scattered into the line of sight, is precisely perpendicular to the radio jet, which means that the photon's last flight before being scattered into the line of sight was precisely parallel to the radio jet, which almost tells you right there that the other directions are blocked. And that leads you directly to, okay, there's a torus. There's a dust ring around this, and it looks like a quasar from other directions. And here is a much more beautiful illustration where the permitted and forbidden lines have the same width. And Joe Miller and I found that when you measure the polarized flux, which, you know, polarization in those days usually implied synchrotron radiation. And it took us a long time to figure this out. It's embarrassing. But gradually we figured out that this polarization was due to scattering. And when you just plot the polarized light, it looks entirely different. In fact, it looks just like a type 1. And the position angle, again, is perpendicular to the system axis. So this is pretty robust. And then, after I left grad school, he did something very clever with Goodrich and Matthews. What we said in our paper is, our scattered lines are broad, but the breadth comes from the convolution of their intrinsic breadth and the velocity dispersion of the scatterers. And since we determined that they were electrons, they could add significantly to the width of the line. So after I left, and so we said in the paper, we don't know if we're looking at hot scatterers or cold scatterers. So after I left, Joe said, I'm going to look at the nucleus through cold scatterers, and he measured the polarized flux off dust clouds away from the nucleus. And they blew in the polarized flux like in a reflection nebula, and the lines are considerably narrower. And you can see this nucleus from any direction you want. This is just two of the things from his paper. And, you know, people discuss what an object looks like from various inclinations, but you can actually measure it, what it looks like from various inclinations. Okay, so anyway, you know the gist of the unified model that seems robust, but I would say relatively trivial because it doesn't get at the energy source. Here's your dust, and here is what people call the accretion disk. I would say the putative disk. I have nothing against it, but it certainly doesn't have the properties of the quasistatic disk that people imagine. Here is a beautiful example of ionization cones, NGC 5252. You can see the hidden type 1 in the center, and then these beautiful cones show the opening. These are crepuscular rays. And this also tells you something about the time history, perhaps, of the AGN emission. And similarly, with HST, you can get polarization, low-quality polarization data, and this shows what you'd expect, polarization cone in a radio galaxy. Now, the reason I got into this subject was because of the beauty of the radio galaxies. And look at that. I just thought, I just fell in love with that when I saw it. And people were astonished to determine that the minimum energy in lobes like this is 10 to the 61 ergs, which is like 10 to the 7th solar masses. That's assuming that God is cheap, if I may be crude. That if you want to make this if you want to make this luminous source and put as little energy in as possible, how will you divide your energy up into magnetic field and electrons? And the answer is roughly half and half, but not exactly half and half. So if God is cheap, it only costs 10 to the 61 ergs to do this. But it could be more. No one knows that it's in the minimum energy condition. Just some more, just because these make me happy. Here's one in which HST shows what could be a torus in the center. I don't know if this is the actual torus. By the way, in the unified model, torus means only one thing. People have used torus for so many things, for the size of the mass distribution or whatever, but it only means one thing in the unified model, and that is in the axisymmetric approximation, it makes a shadow of an optical in the optical band. So it doesn't have to be, there's no physical model attached to it. It just has to be in the axisymmetric approximation something that preferentially lets light out in the polar directions. So there's absolutely no physics in the unified model, which Joe Miller called the unified cartoon. So theorists carelessly use this word, I think. Okay, this is an FR1 radio galaxy nearby. If you look, many FR1s were shown by, okay, I often read that FR1s have, are below, say, 10 to the minus 3 Eddington, and maybe they don't have broad line regions. The truth is, in many cases, we do see broad line regions, and they're almost always in highly core-dominant objects, as though the opening angle is very small. This is not a highly core-dominant object, but it has the HST torus, and it's warm. I was wondering if it had a hidden broadline region, and the answer is it has a kind of a pathetic one, I guess. I don't know. I think, as far as I know, the BLR and the BBB go together, and I don't know what to make of this. See, I basically, most people would say below 10 to the minus 3 Eddington or so, the accretion mechanism changes and becomes inefficient, and you get low ionization. And I basically agree, but I don't feel great about it, because BLAC itself, as you know, will quickly sprout broad emission lines. And so there's a little more to it than that. And, okay, now, true type 2s. I was looking at, everyone references my 1993 review, which I'm very grateful for, but I wrote an update 20 years later, and no one references that, ever. And it's updated. And one thing the editor made me put into that review was a commentary on true 2s. And I noticed this is in both the first and the second of the review papers, that many people assert that there are type 2s that have hidden broadline regions and type 2s that don't. And those arguments always seem very weak to me. And this is supposed to be the champion. This was supposed to be the champion. As you see, 3147, which was touted by Bianchi and many others, We confirm with high confidence this is a true type 2 Seyfert with absence of this. Well, if you look at the spectra of these, they're completely starlight dominated. So you can't see an AGN continuum with no broad line. That's not how the game is played. They're completely starlight dominated. The reason why they say this is a true type 2 is because they say as a proxy for the big blue bump, we're going to use the X-ray continuum. And okay, well, that's not exactly the same thing, but it'd be interesting to know if the broad lines are weak compared to the X-ray continuum in some class of objects. Here's this true 2. Netzer has a review paper on the unified model in which he says 30% of type 2s lack hidden broadline regions. And that's based on nothing. Nothing. And so here was this best one, and this group says this really proves that there exist such objects. The same test was done by Stern and Leor, and they said the upper limit that you put on a broad line in this object is actually not very strong, and it is consistent with what you would expect from the X-ray. They were sympathetic to type 2s, but they didn't think this one really nailed it. So a year ago, I wrote to both of them, and I said, why do you guys disagree? And 2, why don't we look at it all together with 0.1 arc-second aperture to get rid of that starlight? And Leor said, we disagree we're using the same optical spectrum. Our upper limits on the broad line flux differ by a factor of 85. So Stern and Leor were 85 times as conservative. And that's why they said that this was not compelling. Well, here's the spectrum in the little aperture, the little HST aperture. And again, I mean, I don't mind if there are true Seyfert 2s, but I haven't seen a good argument for one. And if you look at my updated review paper from 2012, you'll see my arguments that this particular one would show the broad lines and that others would as well. And this also goes along with the idea that when you have low, low, low L over L edge, you have a really broad line. Okay, I better hurry up. Okay, here there are people that work on galaxy formation and galaxy feedback. In the 80s and 90s, people were excited that if you look at distant radio galaxies, they're elongated in optical pictures, and the elongation is roughly along the radio axis. And some of them are highly polarized. So why are they highly polarized? Well, with a group led by Arjun Day and Andrea Chamati, we did slit spectral polarization of these at Keck, and it turned out to be very interesting. Here, we did some at a redshift of 1 and 2, and they all showed the quasars in polarized flux exactly standard. And we did 2 at a redshift of 4, and they were pure starlight, pure unpolarized starlight. So you can get so much more information when you study these distant galaxies with the polarization optics in. And this is a case, well, I better skip through. This is 1068 versus one of these distant radio galaxies, and it argues that, like 1068, this is Thomson scattering. And that has some remarkable implications in the case of the high Z, but I think I better get going. Okay, let's see. What else? There. Oops, there. Okay. And now, here is something that I called très chic, mais est important, or something. I took French in 7th grade, so I don't really know it, but I like to use it, you know, even if I'm using it wrong. And there have been this is just something that maybe you haven't seen. But I think it's very cute, but I don't know if it means anything or if it's important. There has been mid-IR polarimetry of many radio galaxies, and they're highly polarized, and all the papers interpret it as synchrotron polarization from the extension of the radio core. But I looked at those models very carefully, and I thought that they were basically unphysical. And so with Lopez Rodriguez, we took advantage of the fact that there is now, you can now do far IR polarimetry on the Sophia Airborne Telescope. Here, I think I also like this because of the beautiful colors he chose. Here is the radio core spectrum and total flux. Here's the spectrum and total flux, the radio core. And then this emission is dust emission from the putative torus, let's say. So this mid-IR point had been measured previously, and it was connected to the radio core, even though the radio core polarization at 1 millimeter is vanishingly small. But basically the point is that this now looks like the dust bump. So we're almost certain the polarized flux, the dust is polarized 10% throughout the infrared. And that means that there's a coherent global poloidal magnetic field aligning along asymmetric grains, you know, little pieces of rice. And these points here are to compare the shape of the polarized flux versus the total flux. So the dust bump is 10% polarized in this radio galaxy and in one other, and in all the, both in the mid-IR and the far IR. In radio quiets, this is, we know that the, in the mid-IR, we know that the radio louds are highly polarized, but not the radio quiets, and that was interpreted as synchrotron. But now I think it's because the dust tori are highly polarized in the radio louds by a global poloidal magnetic field, but not the radio quiets. And finally, there's a, okay, how many, 0 minutes? I have 0 minutes. Oh, I'm sorry. Oh, okay. 2 more minutes. One is, in the unified model, there are 1 million papers testing the unified model. And about 1% of those select on an isotropic property. Like if you select on lobe luminosity, that's totally fair. It's independent of angle. But if you select in the two in any different way, that's not independent of orientation, then the result is unintelligible. And I stop reading because I think it's just impossible to interpret. And in the early days of the unified model, people said, well, Seyfert 2s have stronger 5007 lines. And this sample in 1994 was selected by 60 micron, an isotropic property. And so this shows that if you do that, the luminosities of the 1s and 2s, look how perfectly they match. Everything works great, and you get an interpretable answer if you select on an isotropic property. That's the point. And if you don't, and it's unintelligible to me. And okay, well, I went over. I have a dirty little secret, and there it is. And I won't talk about it because I've used up my time.
Questions, comments? Think a little bit, maybe.
Yeah.
Remember, it's $20.
Yeah. So not for that. I saw from your first examples that you were outlining how polarization washes out any atomic features.
It removes them because they're unpolarized, if they're unpolarized.
Yes, but I know that
It doesn't wash them out.
No.
They're just not there. They're not polarized.
Yes, there are some cases where polarization of the bird lights has been studied.
Absolutely, absolutely. It was hard to find those.
Yes.
Poor Makoto did a big survey to find ones with unpolarized lines. That's right. It's not automatic to get those. That was luck and Makoto's hard work surveying.
So that is probably the effect of some very favorable conditions for which that source is observed.
That's true. Perhaps there's a more asymmetry, or scattering is on a smaller scale. Yes, it took a lot of work to find those beauties that had no dust and no line polarization. So, does anyone have any idea of how we could solve quasars before I die? Because I really don't.
Maybe we should mount a polarimeter also on the Apache point that is doing that, and repeat the slow one.
Yeah, why not? I mean, if you're looking at all the time spent on infrared galaxies, imaging and spectra of them, and then someone looks at it with the polarization optics, and you see right away that, okay, that's a quasar, and or not, and or if you use polarization and you see you got unpolarized lines, and you say, oh, God has given me something where I can tell the true spectral. And I mean, there's so many. Not everything is polarized, but it doesn't really cost you anything. So it's frustrating to me that more people don't do it.
So what's the most compelling thing to do, in your opinion?
Well, here's what I would like to do as an observer is when we did the spectropolarimetry to look for the Balmer edge in absorption, I wanted that we picked redshift such that the Balmer edge would be right in the middle of the spectrum. Then I would like to do higher redshift and see what the spectrum looks like under the whole small blue bone through Lyman alpha and beyond. But the brains of my operations is Makoto, and he wanted to do infrared interferometry instead. And I couldn't do it without him. That's what I would have liked to do. I would have said, as an observer, if the one thing I can contribute is the whole SCD of the central engine, then I could die peacefully, because even if it can't be figured out, I contributed something at least to aim for. So that would have been the most important. This thing, we looked at one quasar. There was a theory by Leor, Netzer, and Perron that said in a disk, it was thought 20 years ago that disks had pure scatter, or had not, scattering atmospheres in the interiors, in the inner annuli, and then gradually in the outer annuli stimuli, they were more absorptive. But then, as you go in wavelength, it was thought at a micron, the atmospheric opacity is absorptive in the model, and then it gradually becomes more and more scattering until you get to 912 angstroms. And at 912 angstroms, a new opacity mechanism starts, bound free opacity. So you're now absorption dominated again. And so their prediction, Leor, Nesser, and Prime, was you should see low polarization rising to the Lyman edge, and then below the Lyman edge, the polarization should be killed. So we did that with HST, and what's supposed to happen is the polarization is supposed to go, unfortunately, let's see, oh, this is the Lyman edge. What happens is the polarization is actually constant throughout the optical instead of growing to the edge, and then past the edge, sometimes it goes completely crazy. And here's the polarized flux. So, but we don't talk about that much because HST doesn't have any, it can't repeat that. And the guy who built the polarimeter, Richard Allen, reduced it with his own software and got the same answer. And you know, the fact that the Lyman line is there suggests that it's not just scattered light in the instrument, and there has been zero reports of any such anomalies with this FOS spectropolarimeter. But still, I tell theorists not to look at it.
Okay, if there are no other questions, he will be in Stefano's office until Friday.
Yes, and
by time.
And I apologize for being so depressing, but I'm kind of depressed. I think it's really the climate that's literally the climate that's depressing me. We just seem so doomed, and I'm so worried about it.
Okay.
Okay.
Thank you very much.
So that was okay, I guess.
You were in time. Great.
When do I go to
Florence, what time is the train?
At 10 minutes before 6.
Oh,
so I
10.
think that we have to leave. We have to leave from the airport at the same time because you need to take your trolley. You go to the hotel, you take your trolley, and take you to the railway station.
So we leave at what time? We're going to be 5. Okay. Yeah. Let's.
Non c'è problema, io sono in ufficio di Stato.
Ok.
Cosa? Stavo dicendo che bisogna finire il idem. Grazie.
Te l'ho mandato il link.
Ma non so perché devi essere un scientist di quelli abbastanza.
No.
Sul link
È bello, però se poi.
ma non serve a niente.
No, però per
basta avere una frizione.
Sì, infatti lui dice che basta mangiare.
Io non lo metto.
Ma ce l'ha veramente. Quanti pezzi siamo a disposizione? Tantissimo, per ricordo. Ci vediamo. Sappi che se non c'è tutte le interpretazioni di fisica che devi conoscere più basic.
Quindi forse capiamo qualcosa in più.
Sì, ci sono possibilità di fare proprio questo. Lo stagni? Sì. Oh, giovedì lo stagni? Sì. No, sì, no, voci.
E qual è voce?
Aula S.
Devi entrare
Devi entrare dall'ingresso principale. Principale a sinistra ed è la prima aula sulla sinistra.
Vabbè, niente, allora ci vediamo domani.
Cosa ci fai domani?
Non voglio romperti le scatole perché era tanto tempo che non le rompevo. Ho preso il foglione acciaio, adesso non è esclusa, basta solo guidare la tua macchina.
Mi sa di no perché ti rimane poco tempo.
Vabbè. Ciao.
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 E adesso sentiamo questa.
No, cioè nel senso che secondo lui è una cosa di breve. Ti dirò che non è una cosa in breve che è in campo.
Sì, sì. Va bene. Perché mi nomini? Perché mi evochi e compaio?
Viene del tuo peggio cileno già. Ragazzi, mancavano 70 esaminazioni che non abbiamo le galere, sta roba. Mi ha